like to do today is to start out in a new chapter with a new idea. And again, if you recall, what we like to do is to start more or less from the beginning of an idea and build on up from there. And we're going to be concerned with areas that you might consider in the area of analytic geometry. And in this lesson, what we'd like to do is to talk about the distance formula and also midpoint of a line segment. All right? So let's see how it goes. Way back when, you had an idea that had to do with a right triangle. Let's call it ABC, in which we have here a right angle C, in which let's decide to call the side opposite angle A, little a, and here's a little c, and a little b. And there was a very famous theorem which you learned, which says what? If triangle ABC is a right triangle, then we can come to what conclusion? And Glenn?
A squared plus B squared equals C.
A squared plus B squared is equal to C squared. And what was the name that we gave this theorem, Doug?
Pythagorean.
This is called our Pythagorean theorem. Okay, the Pythagorean theorem. Actually, not only do we have the Pythagorean theorem, but we may also think in terms of its converse, which is also a true statement. And what then would the converse of the statement be? But Peter?
If A squared plus B squared equals C squared.
If A squared plus B squared is equal to C squared, that is, all right, yes?
Then the triangle ABC is right.
Then triangle ABC is right. It is a right triangle. That is, given a triangle in which the sides are A, B, and C is the hypotenuse. Is that right? We've agreed that C then is the hypotenuse. That if this relationship is true, then indeed the triangle is a right triangle. Well, let's utilize that idea and come up with a formula for the distance between any 2 points. Now, you and I have, I believe, already considered a situation such as this. But let's draw the line segments joining these 2 points, which are vertical, and a horizontal line intersecting at some point. Let's call it R. And
it would be x2, y1.
x sub 2, it would have the same x coordinate as point P sub 2, and would have the same y coordinate as P sub 1, which is y sub 1. Is that right? Now, let's consider the distance from P sub 1 to R, and we certainly know all about distance along the line segment, which is parallel to an axis. And what then can we say about that distance, Peter?
X sub 2 minus x sub, the absolute value of x sub 2 minus x sub 1.
Good. Let's talk about the x sub 1. Does everyone agree we may also write that as the absolute value of x sub 1 minus x sub 2? All right. Now, what then would be the distance from P sub 2 to R, or else from R to P sub 2? How may we think about that? Tim?
The absolute value of y sub 2 minus y sub 1.
Minus y sub 1. Does everyone agree with that? Now, just looking at our triangle as we have here, this is certainly a right triangle, and now we know the length of this line segment, and we know the length of this line segment. Therefore, I think you will agree that we may find the length of this line segment, P sub 1, P sub 2. Now, there's a notational device that we use, and let's use this device, the distance from P sub 1 to P sub 2. All right, and using this notation, we know then that this number squared from our Pythagorean theorem must be equal to what? And what may we say? But that it is equal to, anyone here, Bill?
X sub 2 minus x sub 1.
All right, let's
squared.
the quantity squared. Let's indeed include this in terms of our absolute value. All right, the absolute value of x sub 2 minus x sub 1 all squared.
Plus the absolute value of y sub 2 minus y sub 1. All squared.
Y sub 2 minus 1 all squared. Now, what do we know about the absolute value of a number squared? Well, what do we know about the absolute value of any number? The absolute value is always positive, and indeed any number which is squared is always what kind of a number? It's always positive. So what then may we say about this statement? May we simply eliminate the absolute value symbols and write this simply as what? Here we have what? X sub 2 minus x sub 1, the quantity squared, plus, and here we may write what? Y sub 2 minus y sub 1, the quantity squared. Now, this then is the distance of this between these 2 points all squared. If we then were to simply take the positive square root and talk about the distance from P sub 1 to P sub 2, we always think of distance as a positive number, or certainly non-negative number. It then would be the positive square root of what? of what we see here, namely, Dick,
X sub 2 minus X sub 1
x sub 2 minus x sub 1,
plus,
all squared,
right, squared plus Y sub 2 minus Y sub 1 all squared.
y sub 2 minus y sub 1, all squared. And in fact, this statement as we have here, we may give a name which you and I recognize as the distance formula between any 2 points, P sub 1 and P sub 2. All right? Well, let's now turn to the second idea of this lesson, in which we would like to be able to come up with the coordinates of some point M, which is the midpoint of a segment from P sub 1 to P sub 2. And in fact, I don't think this is anything new. Perhaps it's worth our while to try to prove this, but does anyone happen to remember what the coordinates of any point, in this case the midpoint M, is for a given segment? And Peter?
X plus X sub 1 plus X sub 2 over 2.
All right, x sub 1 plus x sub 2 over 2, the average of the x coordinates, so to speak.
And Y sub 1 plus Y sub 2 divided by 2.
Y sub 1 plus y sub 2 divided by 2, the average of the y coordinates. All right? Now, certainly, I think perhaps it's quite obvious that these are the coordinates of the midpoint. Let's prove it. Let's see if we can't prove it. And I think perhaps there's more value in our considering the proof and how those ideas go, rather than simply looking at the coordinates of the midpoint. Now, let's see how we can prove it. We can either rely on the distance formula completely and say that this segment, this distance is equal to that distance, but that won't necessarily tell us anything about the fact that it's a straight line. So I think then you would have to go on and show one more statement, namely that what? That not only is this segment is equal to this segment, but you should also show, what, Bill?
That their slopes are equal.
That indeed their slopes are equal. If their slopes are equal, what then does that show? That shows that, Doug?
It's one line.
It's one line. Is there another way in which you can show that it is one line, other than by slope? How about, well, I think from your work in geometry, Doug?
Could you determine a function for that line, see if the point M is on, satisfies that function?
Okay, I think perhaps that's another way out, and I think perhaps a bit more difficult than the idea that I had in mind. How about simply showing that this segment plus this segment is equal to that segment? And if you were to do so, what then would that show but that it is what? It is a straight line. Is that right? Let's try the slope approach first. That is, let's talk about the slope of P sub 1 comma M. And we would like to show that this is equal to what slope? Oh, let's say P sub 1 comma P sub 2. Is that right? Or P sub 1, P sub 2, that segment. Well, what then is the slope of P sub 1 M? And P sub 1 M is the change of the y values, right? Which is what? We may think in terms of what? Y sub 1 plus y sub 2 divided by 2 minus what coordinate here? Y sub 1 divided by, now the corresponding change in the x coordinates is going to be what? X sub 1 plus x sub 2 divided by 2 minus x sub 1. All right, now let's simplify this right-hand side and see where it leads us. Let's multiply top and bottom by some number. Another name for the number 1, which is, Bill?
2 over 2.
2 over 2, all right, times 1, where the name for 1 is 2 over 2. 2 times this numerator then is going to give us what? We have there, Dick?
Y sub 1 plus Y sub 2 minus Y sub 1.
Minus, careful there, we're 2 times the y sub 1 is a minus 2y sub 1 all over, Dick?
X sub 1 plus X sub 2 minus 2X sub 1.
Minus a 2x sub 1. Everyone agrees with that? All right, now let's look at this and notice that y sub 1 minus a 2y sub 1 may be written as, here we have a y sub 2 minus a y sub 1 divided by what? X sub 2 minus x sub 1. But looking at that and coming back to our picture, what do you recognize this statement as? This expression as? What is that but a name for, Don?
The slope of P1.
That then is the slope of P sub 1, what? P sub 2. Is that right? The segment P sub 1, P sub 2. Now what then have we shown thus far? What have we shown by showing that these two slope numbers are equal? This is just half of our statement, which we want to prove. Bill?
You proved that point M is on that line.
We've proved that point M is on the line. Now let's turn to, say, the distance formula, and let's talk about the distance from, say, P sub 1 to M. And what would we like to show that this distance is equal to? But what? This distance we would like to show is what? 1/2 of the total distance, is that right? So let's indeed try to do that. The distance from P sub 1 to P sub n, let me use the notation of P sub 1 comma m. And what then would we say about that? It's the square root of what? Well, it's the difference of the x-coordinate squared, which is going to be what? What may we say there? It's what? X sub 1 plus x sub 2 divided by 2 minus x sub 1 all squared plus what? Y sub 1 plus y sub 2 all over 2 minus y sub 1 all squared. Everyone agrees with that? Is equal to. Now, let's see if we can't simplify what is inside the parentheses first. And let's get this all over the same denominator of what? Of 2. And when we do so, we have what? X sub 1 plus x sub 2 minus what? 2x sub 1 all over 2, the quantity squared, plus what? Y sub 1 plus y sub 2 minus a 2y sub 1 all over 2, that quantity squared. Now, let's look at that numerator and see what we have. And what do you see in there but a name for, John? X sub 2, good. X sub 2 minus x sub 1 all squared. Let's now put this number all over what in the denominator? All over 4. Plus, and now what then is a name for what we have here, Kirby? What do you see there?
Y sub 1, Y sub 2.
Y sub 2
Minus Y sub 1.
minus y sub 1
All squared.
all squared
All over 4.
all over 4. Now, looking at that, notice there is the same denominator of 4, and without putting in another step, we may factor that denominator out, and it's 1 over 4, and the square root of 1/4 times the square root of this, and another name for the square root of 1/4 is 1/2, and what is left but the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared, and you now recognize that as what? Coming back to our figure, what we see there is what? The distance from where to where? From P sub 1 to P sub 2. So in fact, I think we have there 1/2 of the distance from P sub 1 to P sub 2. And is that what we wanted to show? Are we done? Fine. And indeed, we have here the coordinates of the midpoint. Actually, there is a theorem that one can develop, I don't want to do it now, in which we can find the coordinates of any point on a line segment. And there's a nice relationship that one can show in order to do that. Let me give you your homework assignment for next time in which you can practice with some of these ideas.